Okay, it's a great pleasure and honor to introduce the next speaker, the distinguished super-rational researcher, Sergiu Hart. But instead of going to his vita, let us just mention on this occasion of the 20th anniversary of the center that he was the founding director of the center, and he shaped it. And we speak here about small decision, big decision, various layers of the mind. And obviously, as a super-rational decision maker, when it comes to important decision, he spends the time, investigate, he thinks and compute. And so we managed to get the excellent administrative director of the center, Hannah Shemesh, which I know that this was one of the decisions in the center that Sergiu Hart was spending a lot of time and investigation before making this choice. Not like in a seminar where you can make a quick remark without thinking, without calculating. In any case, it just encourages the discussion. But this is an important decision that lasts with us forever, and here we all thank him for making that choice. Sergiu Hart.
Okay. Thank you. In fact, that was one of the easiest, you'll be surprised, but I didn't have to spend a lot of time. When I saw Hannah, I think that was one of the easiest decisions to decide that she's the right person. Okay. Now, let's see. Is that okay, Danny? Danny? Okay. So, before starting to talk on riskiness, don't worry. In a moment, I'll get excited. Okay. Okay. I wanted to show you. Okay. This is the founding document of the center. So Menachem showed you yesterday his proposal, the Tiota, the first draft. And that is the decision of the, for those who don't read Hebrew, also for those who do, Office of the Academic Secretary announcing that the Vada Matmedet, the standing committee, the perpetual committee, they are not perpetual, but that's a name, of the university has decided to establish the Center for the Study of Rationality. And that's what it says here. All the rest is history. Okay. So now, okay. You think I should? Let me try this because I have a hard time standing in one place. No? No good? No good. Just tell me if I go too far away from me. Yes. Okay, so this is going to be an extremely technical talk. Okay, there are going to be equations on every slide of at least 20 symbols. Okay, so I hope you don't expect that because you're not going to get it here. I'm going to try to make things as simple as possible. Of course, you are most welcome to read the more formal material. And what I want is to survey shortly a certain area that has been developed in the last few years, which was started by Bob Aumann over there, and Serrano, and then he developed here at the center. Dean Foster was visiting the center, and we started talking about it. And you can see the papers. By the way, this is on my webpage, so if you are interested, you can just click on it and look at the papers. And let's get to business, okay? So we want to talk about risk, okay? What's the object we want to study? A risky asset, if you want a fancy name. If you want a less fancy name, a gamble. Okay? What's a gamble? Well, a gamble is something like this, where with probability 1/2, I don't know if you can see the red dot. With probability 1/2, you gain $120. With probability 1/2, you lose $100. So those halves are probabilities, okay? Now, just to make it clear what I mean, those are net gains and losses. So that means by how much your wealth increases or decreases. To make things interesting, we are going to look at gambles that have positive expectation and where some losses are possible. If you can only make money and you don't know what to do with it, as I always say, bring those lotteries to me, I'll take care of them, you don't have to worry, okay? So the interesting or the more difficult ones, let's say, or the really interesting ones, where you can lose, but the expectation is positive. Okay? And one has to start someplace, so you start from the very basic situation where the probabilities are known and given and fixed. That's what's called pure risk. Of course, from here one can go to more general models of uncertainty and so on, and in fact, some student at the center, Moti Mikhail, I don't know if he's here, is working on things like this. Now, I'm going to show you 3 different approaches, okay? And I'll start from what I call the ordinal approach. And ordinal means I want to compare such gambles. I want to compare such objects. Namely, you take 2 such objects, a G and an H, like we had on the previous slide. And here is a question. When can I say that G is less risky than H? When can I say that H is more risky than G? I want to say, you know, this is a gamble, this is another. Which one is more risky? Okay? Now, of course, I can say something, and Merle can say something else, and so on. So each one can have his own view. But is there some objective, and I'm going to use this word repeatedly, rather than subjective. So subjective is something that represents how I view things. But is there some objective way, some general way, that one can compare gambles in terms of the riskiness? That's what we are trying to capture. Okay? Now, how do you do that? Okay? So here is an idea, very simple idea, in fact, and it says the following. Let's look at decision makers that hate risk. They are called risk-averse decision makers. Risk-averse, yes? So I'm talking in a way which is not politically correct, saying hate, but I think you say risk-averse, it's very difficult. So let's look at decision makers that are risk-averse, and let's see to which one of the 2 gambles they are less averse. Let's see which one of the 2 gambles they hate less, okay? So the one that risk-averse, so if we look at people that hate risk, the things that they hate less should be less risky, okay? Very easy. Question is, how do we make out of this something operational? How do we make out of this something, okay? How do we put flesh into these words, okay? So let me just start with, let me put in the background the basic decision theoretic model, and which goes back to von Neumann and Morgenstern. Goes back to Bernoulli and so on, as a long history, but in terms of formalization, goes back to von Neumann and Morgenstern. You know, the book on games, the book that started game theory, also has something which started utility theory, okay? The von Neumann-Morgenstern utility theory. And what von Neumann-Morgenstern proposed is a set of desiderata, set of postulates, very simple, I'm not going to get into that, which any rational, and rational here is in quotation marks, decision makers satisfy. And for such decision makers, it's very easy to evaluate gambles. How do they evaluate a gamble? They have a utility function, okay? This may sound complicated, those who never saw it may sound complicated. I will show you an example in a moment. But there is a neat way to compare gambles, okay? Which has the following. You take gamble G, you take gamble H, you look at your wealth, so W represents the current wealth. Remember that gambles tell you how much your wealth increases or decreases. Therefore, if you start at W, you are going to end up at W plus G if you are in G, or at W plus H if you are at H. And then you compute the utility of that, and since these include probabilities, you have to take expectations, okay? Now, that may sound very complicated, so here is a very simple example, just so you see that this is a very simple formula. So here are just 2 gambles. When is our decision maker going to prefer the left one to the right one? Okay? On the left, he computes the following. 1/2 times the utility of W plus 300. and 1/2 the utility of W minus 100. On the right, he computes 1/4 the utility of W plus 500 and 3/4 the utility of W minus 200. If the first number is greater than the second, then he prefers the first to the second. That's expected utility, very simple, okay? Now, remember, we want to talk about risk. If we want to talk about risk, we want to look at decision makers that hate risk, that are risk averse. Okay? What does risk aversion mean? Something very, very simple. Risk averse in this framework is very simple. Look at this gamble again. 1/2, you gain 300, with probability 1/2, you lose 100. And compare this to plus 100. Now, what is plus 100? Plus 100 is exactly the expectation, the average that you are going to get. With probability 1/2, you gain 300. That's 150 on the average. With probability 1/2, you lose 100. That's minus 50. 150 minus 50 is 100. It's a little easier than 17 times 24. So I think that your pupils only increased by 25%. Okay. So if you always prefer to get $100 for sure, rather than getting some lottery where you get $100 on average, that means that you hate risk. Okay? In terms of the utility function, if you remember the previous slide, it translates into this trivial inequality. And this simple, I won't say trivial, into this simple inequality. And this simple inequality just says that the function is concave. Okay? So risk aversion means the utility function is concave. Okay? That's a nice mathematical characterization. What it means, again, is the following simple thing. If you are given a choice between getting a certain amount of money for sure and getting a lottery where you get the same amount of money on average only, but sometimes you can get more and sometimes you can get less, even lose, you prefer to get it for sure. Okay? That's risk aversion. Nothing more. Okay, so let's go back to what we wanted to do, which is to compare risks in terms of looking when risk-averse decision makers hate G less than they hate H. When risk-averse decision makers are less averse to G than to H. Yes, I mean, to negation is always difficult. So, you know the story, I think, about this seminar in logic, you know, where I think it's where the speaker was saying it's very surprising that double negation is positive, whereas double positive is not a negation. Somebody from the back of the room said, yeah. That's somebody, I think it's Morgenbester. Sidney Morgenbester, is that? Yeah, yes, sorry, I can't reproduce the accent, but okay. So anyway, what I want to translate is that thing that people that hate risk hate G less than they hate H, okay? So how do we do it? Very simple. Since we take all people that hate risk, okay, and we require that everybody that hates risk, when given a choice between G and H, they will choose G, which translates into this very simple formula. Doesn't matter, you don't have to read the formula. What it says, if you remember the previous slide, is that everybody who hates risk, when given a choice between G and H, they take G. They prefer G to H. Okay? If that happens, that means everybody prefers G to H. That's a clear sign that if everybody who hates risks prefers G to H, then clearly G has less risk, is less risky than H. Okay? Now, this turns out to be a well-known property, and that's called stochastic dominance of the second degree, okay? Which sounds terrible, but in fact embodies something very, very simple. And let me explain to you what this is, okay? And I'll do it by example, okay? If you take two lotteries that look exactly the same, except in some instances you are getting more money, clearly you'll prefer the one where you get more money. For example, here on the left, with probability half you get $200, with the same probability on the right you only get 150. All the rest is the same. So clearly everybody will prefer the left gamble to the right gamble. Okay? Good. Forget that. Suppose that suppose that you gain 200 with probability half, but on the left you lose 100, on the right you lose 120. Clearly you would rather lose 100 than 120. Again, everybody prefers that. Okay? This is a little more subtle. let me not get into it. The probability of gaining has decreased. The probability of losing has increased. Again, that goes under this. You can move probability of 6 from one side to the other. Okay? But that's not all. Suppose that you look now on the left. On the left, with probability of half, you get to 100. With probability of half, you lose 100. That's constant. Instead of that, let's take this to 100, and you are going to get either 250 or 150, and now it's probability a quarter, which is a half of a half. Okay? Clearly, you'd rather get the 200 than this average between 250 and 150. Okay? Now, this thing is called a mean preserving spread. Okay? Mean is not something nasty, but mean is average. Okay? So that says it's a spread where you keep the average constant. And so from left to right, you have a mean preserving spread. And mean preserving spreads, which means replacing something sure by a lottery, is something that risk-averse people do not like. That's what makes them risk-averse. Now, it turns out that the stochastic dominance that we get from the previous, or 2 slides ago, exactly amounts to the operation, to the kind of transformation we talked. So G dominates H, if and only if you can go, if and only if in G you have higher gains, or lower losses, or less lotteries, which is clearly something that everybody prefers. The beauty is that that's all. There is nothing else. I mean, that's not a completely trivial theorem, but that's a classic theorem. Okay? What's the problem with stochastic dominance? I mean, it's so nice, it's so beautiful, everybody agrees, there is no dispute. The problem is that if you take 2 gambles, and here I just took 2 gambles, people are not going to agree. One is going to say left is better than right, or I prefer left to right. The other is going to say I prefer right to left, and that's it. We don't get any conclusion in terms of stochastic dominance. Formally, what it says is stochastic dominance is a very partial order. And here, very, of course, it's a quantitative statement. Most pairs cannot be compared. It's quite rare that you can compare pairs of gambles, because remember, there are only few transformations that can give you stochastic dominance. So what do we do? Well, one thing is we can go home and say, that's it, that's the end, we cannot say anything more, that's how life is. Okay? But I think we can say a little more. And I'll try to convince you that one can say a little more. Okay? So for this, let me add another small thing. I say you are given 2 gambles, G and H, and you decide, do you want G or do you want H? But you know, when you are given a gamble, you are also allowed to say, I don't want G, I don't want H. You are offered the gamble. Unless you are a compulsive gambler, you can say no, and some people say no. When are you going to say yes or no? Very easy. I mean, if your expected utility from accepting the gamble, which is the expression on the left, is bigger than the utility that you have when you stay at your wells, then you accept. If it's smaller, you reject. Very simple, okay? So now, I'm saying this. Suppose I'm giving you 2 gambles and ask you which one you prefer. And you think, compute, level 2, whatever, and you say, prefer G, okay? But in fact, you would not accept neither G nor H. So why do I really care that if I were to force you, you would prefer G to H? In fact, you don't want G and you don't want H. You reject both of them. So that suggests the following criterion. Let's not ask people about what they prefer, but let's just see what people accept and reject. And if a gamble is rejected more by risk-averse people, that means it's more risky. Okay? So here is the next way to translate operationally this statement that I wanted, that risk-averse decision makers are less averse to G than to H, in just saying that G is rejected less than H. Okay? What does this mean? It means something very simple. You take any concave, all utility functions are concave. We are only talking about risk-averse decision makers. So I put in parentheses because at some point I'll stop saying concave, but it's always concave, okay? For every concave utility function, if somebody rejects G, then he also rejects H. So H is rejected more than G. Whenever G is rejected, H is also rejected. But it could be that G is accepted, whereas H is rejected. Okay? That's okay. Both could be accepted, okay? But if G is rejected, for sure H is rejected. The set of rejections of H is larger. H is rejected more often, okay? In this very clear sense. And if you don't like words, you can see formulas, but I think words are just as good as formulas in this respect, okay? That's what it says. If G is rejected, then H is rejected, okay? Now that gives us a new order between gambles, which I call acceptance domination, okay? Notice one thing, that it extends stochastic dominance. Why? Because if everybody prefers G to H, that means that this expression here is above this expression, not just in terms of where it is on the slide, but also in terms of being a higher number. Okay, this number is a higher number than this one. If everybody prefers G to H, this is bigger than this. So if this number is less than U of W, then the number below is surely below U of W. Okay? Now this very complicated mathematical argument, okay, shows that if everybody prefers G to H, then necessarily H is going to be rejected more than G. On the other hand, it could well happen that H is rejected more than G without having stochastic dominance. So we are extending stochastic dominance. How much? Unfortunately, not by much. One gets some interesting things here I'm not going to talk about, but we are still in the situation that most gambles cannot be compared, even in this more extended sense. Why is that so? Let's try to understand. The reason is we say, let's look at the last definition. Any time, any decision maker, any utility and wealth where G is rejected, H should be rejected. Every time. That's a very stringent requirement. That's why it's very hard to satisfy. So let's make the requirement a little more reasonable and say, look, the fact that there is one specific rejection, okay, there is a rejection. Somebody, some utility and someone else rejects, okay. Let's not, that doesn't say enough. But if we have substantive rejection, there is rejection not by just in one instance, but in a whole set, in a whole collection of instances, if there is a certain serious rejection, substantive rejection, uniform rejection, in many, many instances of G, okay, that we should take seriously. And then we want that such serious rejections for H should be more often than for G. So rather than looking at the level of a single rejection, let's look only at serious rejections, serious in quotation marks, namely uniform rejections. Now, what does it mean, uniform rejections? There are many ways to do it. There are two simple ways to do it, and I like to do things simply. After that, one can complicate, okay? But simply, a decision is characterized by two things, the utility function and the wealth level. So we can do uniformity on one or the other. So let's try. So first attempt is to say the following. We are going to say that risk-averse decision makers hate G less than they hate H if they reject G less than H in the wealth uniform sense. So if it happens that G is rejected by a certain utility function at all wealth levels, that means not just at one, but always, no matter what the wealth is, that decision maker, that utility function rejects G. That's significant rejection, right? If that happens, then the same should happen for H. That means that in this strong sense of rejection, H is rejected more often than G. Okay? This is the formula, of course, doesn't matter. That's written in words just as well. And that gives us a new order, which I call wealth uniform domination. One can do the dual thing, namely to say, let's look at rejection that is uniform over all utilities, which means if there is a certain wealth level where all utility functions are rejecting G, then at the same wealth level, all utility functions should reject H. That means that H is rejected more than G in the utility uniform sense. Okay? That gives us, again, it's written here, that gives us a new order, utility uniform domination. Now, both orders are okay, so what have we done? What have we done is to say that one gamble is less risky than another if it is rejected less often. Now, what do we mean by rejection? Rejection could be in a single case, which means by one utility at one wealth level, or could be rejection in a wealth uniform sense, which means rejection by one utility at all wealth levels, or could be in a wealth uniform sense, in a utility uniform sense, rejection by all utilities at one wealth level. I hope I didn't say the same thing twice, but you get the picture, okay? And notice, let me remind you, we started with stochastic dominance. If we have stochastic dominance, we automatically had what I called acceptance dominance. And since acceptance dominance says rejection here implies rejection here, then clearly a whole uniform rejection here will imply the whole uniform rejection here. Just do it case by case. So clearly those two things are extensions of stochastic dominance. So we have extended stochastic dominance, which means hopefully we can compare a few more pairs of gambles and can say which one is more risky than the other. Okay? So let me give you the results. Okay? The results of the jury, yes, or whatever you want. So let's take Wells uniform dominance and utility uniform dominance. Those are two different orders. Turns out that Wells uniform dominance is a complete order, which means, unlike stochastic dominance, unlike acceptance dominance, you take any pair of gambles G and H, and either G dominates H or H dominates G. Okay? You don't like it, Eud? You're surprised. Very good. I like people to be surprised. Yes. Sorry? Yes, it is, because set of inequalities implies another, you cannot have the opposite. You'll figure it out, I'm sure. I give you 10 seconds. Yes, yes, it is clear. But the surprising fact, and in fact, I mean, I was surprised myself. Yes, so I'm glad that Eud is also surprised. I mean, this modification of going to uniform rejection suddenly allows us to compare any pairs of gambles. Okay? If you take any G and H, either G will dominate H or H will dominate G. There is no indeterminacy in this comparison. Okay? Unlike stochastic dominance, which I said, very few pairs you can compare. Most pairs you look at G and H and say, I can't say anything. How about utility uniform dominance? It's also a complete order. Okay? Now, even more. If we have an order, then the more formal people here will immediately think order like preference sort and so on. There is a way to represent it with an index. Right? Namely, if we have a complete order, then one is bigger than the other if the index is bigger. Okay? And turns out there is such an index that represents this order. Namely, the Wells uniform dominance is exactly equivalent to the order induced by the Aumann-Serrano Index of Riskiness. That was the first paper that I mentioned in the list of papers. Okay? I'll tell you what that is. But formally, what the index of riskiness of Aumann and Serrano is, it associates to every gamble a number, a real number, a positive number in fact, which measures in the Aumann-Serrano sense, and I'll explain to you in a moment what that sense is, measures the degree of riskiness that is embodied in that gamble. And the one that has a higher degree of riskiness, okay, so, sorry, I keep pointing here, yes. The one that has the higher degree of riskiness is clearly, or the one that has a less degree of riskiness is the one that is preferred. Okay, dominance goes the opposite way, because dominance is the better one, whereas riskiness is the more risky. So that's why the inequalities go the opposite way, but it's an if and only if. Okay? So higher Aumann-Serrano exactly corresponds to this order. Utility uniform dominance also has a nice and neat representation, and that's a Foster-Hart measure of riskiness, and which is another positive number that is associated to every gamble that measures the riskiness of the gamble in the Foster-Hart sense, and I'll tell you what that is, and you get the same thing. Okay? If you have more riskiness, it's less preferred. It's dominated. Okay? So not only got complete orders, we also have a neat representation. We have an index that tells us exactly what that order is. You have a G and an H, and you want to know what they are. Compute Aumann-Serrano or Foster-Hart of that, compute of that, and see which one is the bigger number. That's the one that is dominated by the other. Very simple. Now, what are these indices? Okay, Aumann-Serrano and Foster-Hart. So let me start with Aumann-Serrano. It's the following. Okay, look at this formula. Okay, X is exponential and E is expectation. They both start with exp, so I have to distinguish. Okay, so what you do is the following. Think of where it says here RAS of G, put a big X there, unknown, X for unknown. Okay, and think of this as an equation in that X. So what it says the following: you take the gamble, you multiply it by 1 over X. X is a positive number. You take the minus sign, you take XE to that power, subtract 1, it's still a random variable, all the thing, and compute expectations. That gives you an equation. I want this to become 0. And the claim is that there is there is a unique number that fits here, okay? and you immediately say, well, this thing is monotonic in that number, so clearly there is going to be a unique point where it intersects the 0. That's not true. It's not a monotonic function because G can take negative and positive values. Nevertheless, it's slightly more subtle. This equation has a unique solution which determines this number RAS of G. Okay? Foster-Hart looks something similar, but not the same. You take the gamble G, you multiply it by 1 over an unknown, let's call it Y. You add 1, you take log, you take expectation, make it equal 0. Looks terrible. I mean, this is, pulled out of the sleeve, something like this. It's. But those things have nice interpretations, which I'm going to explain to you now. They are written here, so let me start with the Aumann-Serrano. So without getting into technicalities, what time did I start? So what time do I have to end? That's, or I can add an hour, yes. Almost half an hour, okay. Okay, so the Aumann-Serrano is essentially based, essentially captures the following. Aumann-Serrano derived it in a different way, but what they capture is the following. When I have a gamble, some people will accept it, some people reject it. What will determine whether a person accepts it or rejects it? What is that posture of that person to risk? What's the attitude towards risk? So there are people that are, everybody is risk averse, okay? But there are people that are more risk averse, and there are people that are less risk averse, okay? And when I take a gamble, one can find, in a certain sense, exactly at what level of risk aversion of the people there is a switch from accepting to rejecting. And that's exactly what the Aumann-Serrano Index of Riskiness captures, okay? The critical level of risk aversion where if you have more risk aversion than that, you reject. If you have less risk aversion than that, you accept. Sorry? So the way to do it is to go, okay, so since Ehud asked, this is the answer for Ehud. Okay, you read it, but I don't want to go into details, yes? The way to do it, you go through those that, so the Kara people have constant absolute risk aversions, and through them you determine what that is, okay? That's a way to do it formally, but let's not get into it, okay? Because it's technical, that's not supposed to be a technical talk. What about the Foster-Hart measure of riskiness? That's something different, okay? That determines something which I call the critical wealth. That for every gamble associates a certain level of wealth which is critical in some sense. And since I'm going to explain this in the next approach number 2, which I'm coming next, I'm not going to get into detail now, but getting back to the previous slide, the Aumann-Serrano Index captures the critical risk aversion. That utility function that is critical. More risk aversion, rejection, less risk aversion, acceptance. The Foster-Hart measure captures the critical wealth level where something happens. Above it, people accept. Below it, people reject. What is people and so on, we have to understand what it means, okay? So to every gamble, one can associate a critical risk aversion level and the critical wealth level. And that's exactly what those riskiness measures do. Okay? And, okay, let's not, okay? So that we already saw. I'm not going to get into technical details. In order to make all this into real theorems, one needs to make some assumptions on the class of utility functions that one looks at. And in fact, one essentially goes to assumptions that Arrow made in famous 65 paper, where he introduced all this risk aversion, measures of risk aversion, Arrow, Pratt, and so on. And that turns out to be exact. Arrow has two conditions, which are exactly the two conditions needed here. It's quite amazing. That's exactly what is needed here, okay? Let me not get into details. You can look at the paper and so on. So let me summarize this part before I continue, okay, where we are. So the idea was to say that a gamble G is less risky than a gamble H whenever risk-averse agents are less averse to G than to H. And what's aversion? Aversion, for me, means rejection. So that's something very operative, not asking questions. You already know, Danny Kahneman told us, you ask people questions, what you get as an answer has nothing to do with the question that you thought you asked. They answer something else, okay? But let's see what people do. Do they accept or reject? Let's give them a real task, okay? That's something, it's like reveal preference. Let's look at the actions, okay? So aversion, how does somebody express aversion to a gamble? By rejecting it, okay? Something very clear. But I don't want to look at single rejections because that's not enough. A single rejection, it's too little. I want to look at substantive rejections. So comparisons in terms of more rejection or less rejection should be made when there is a substantive evidence of rejection. Okay? So that leads to this definition that G is less risky than H whenever G is uniformly rejected less than H. Okay. Okay? Now, I want to emphasize a few points and which are important. This approach is completely ordinal. Ordinal comes from order, which means comes from I want to compare G and H. Okay? Now, that's different than Aumann-Serrano and Foster-Hart, which associate to every gamble a number. That's cardinal. Okay? So those that know standard decision theory will understand this distinction. But again, here we are only talking about comparisons. That's all. Okay? Second, the comparisons that I got are objective. So it's true that we have we had looked at decisions of risk-averse decision makers and saw what they do. But the answer is independent of any specific decision maker. So this is not something that a specific decision maker does. Okay? It's an objective measure, and I'll come back to this point. It's not a subjective measure. Subjective is asking one person and see what that person wants, G or H. Objective is something general that we are obtaining, something that depends only on the gamble and not on the decision makers. So what enters into those formulas are only when I give you a gamble plus 200, minus 100, half, that's all that enters into the computation. Plus 200, minus 100, and the probabilities. Nothing else. No utilities enter there. Because the utilities have a quantifier for all U or for all W. Okay? We got a complete order. Notice, okay, the reason we succeeded in going beyond stochastic dominance is because we introduced the current wells. Without current wells, if one only looks at the final wells, where I don't care where I came from, one cannot go beyond stochastic dominance. All this exercise is not going to work. This exercise worked only because we are separating current wells and the change in wells. That's what enabled all this to be done. Okay? So again, status quo, we already know that that's an important feature, so that's another thing to take into account. So we got complete objective orders. Okay? And the word objective is crucial here. I'll in a moment talk about it again, because now I want to talk about the operational approach. Okay? And the operational approach, that's what that Dean Foster and myself, Dean was visiting here at the center, and that's when we started working on this after Bob Aumann gave his talk at the center. So all this is really a center, pure center activity, I think. Now other people are of course involved, but it started here. Okay, so we already know what the gamble is. Now what I want to do is the cardinal exercise. Okay? It has nothing to do with the Pope when I say cardinal. Cardinal means I want to associate to every gamble a number that is the content of riskiness of that gamble. Okay? That I want to say this gamble has 200 riskiness. What's 200 riskiness? Okay? Let's see if we can make sense out of it. Okay? So, and again, I emphasize that what we want is an objective measure. Now you'd say, well, I don't know, how can you get something objective? There aren't such things objective. What you have, somebody prefers this, somebody prefers something. How can you get any objective measures? But there are objective measures. If I'd ask you, what's the return of the gamble? Well, it's just the expectation, the average. Now, everybody will get the same, of course, modulo errors in computation and level 1, 2, and so on, but in principle, the expectation of the gamble is a certain objective number, doesn't depend on what you do with it, doesn't depend on how you look at the gamble. The return of the gamble is a certain objective number. If I ask you about the spread of the gamble, the standard deviation, that's an objective measure. Okay, these are objective measures. We want riskiness to be of the same class. It's like, in some sense, a parameter of the distribution that describes the riskiness content of the distribution should be objective. Okay, should depend only on the distribution, should depend only on outcomes and probabilities, nothing else. Okay? Question, can one do it? Okay? Now you'll tell me, well, we already have something like this, standard deviation. Okay? Well, standard deviation is heavily used. It has a big problem. It's not monotonic, which means you can make gains higher, losses lower, and standard deviation will tell you that riskiness is higher, which is clearly stupid. Okay? that translates into not being monotonic, and it's monotonicity with respect to stochastic dominance that we talked before. Now, that's a well-known phenomenon, so unless you are in a very simple, not very stylized world where everything is normally distributed, or maybe log normal or something, and utilities are so and so, that is not going, sorry, forget utility, erase the word utility. When things are normal, random variables, that makes no sense, okay? But that's the only thing that people use. In fact, not the only thing. They use things that are even worse than that. I'll tell you about it, okay? So what we want is a measure of riskiness that is objective, depends only on the gamble, only on values and probabilities. Now, we want to measure it in the same units that the gamble is measured. So if it's in dollars, it should be in dollars. If it's in shekels, it should be in shekels. But we want a little more than that. What we want is that we want the scale of that to be what's called homogeneous of degree 1. It should be scale invariant, which means if I multiply everything by 10, it should be multiplied by 10. It's exactly like E and sigma. It's exactly like all the other things that are for us where we want to go. The return, the standard deviation, all those things are measures that are homogeneous of degree 1. So you change scale, you multiply by that. We would like it to be monotonic in the sense that it should satisfy this very clear thing that higher gains, lower losses, less lotteries, all these things should say that the content of riskiness goes down. If not, then we are missing something, okay? And we want something not, that one can do something with it, okay? Okay, so let's see how we can do it. So let's take again our gamble. I don't know if it's, okay, this gamble, I don't know. Now, suppose that you have $100. That's all you have. That's all you have. Now, taking this gamble is very risky. I mean, you can lose all your money, okay? If you have less than 100, I mean, you'll be completely bankrupt. Now you say, okay, you can always take loans. Okay, in the wells, I already included all the loans. You have gone maximum on your credit cards and everything and so on. That's it. There is no more, okay? So we're taking this into account. That just changes, of course, the origin. But let's assume all you can have access to is $100. Well, you take this gamble, with probability half, you are going to go bankrupt, okay? In England, you go bankrupt, you go to prison for the rest of your life. That's the end of it, yes? Dickens, yes? In fact, I was told that it was not so bad in those days, you could grow your vegetable garden there, and relative to what was outside, it was debtor prison was not such a bad thing. But still, you go bankrupt, you go to debtor prison, and that's it. There is no escape. I mean, there is no way for you to get out, okay? On the other hand, if you have $1 million, is this risky? Now, come on, it's not risky. Remember, I mean, look, this is positive expectation. So, in the worst case, you have $1 million minus $100. Okay, but that's not risky, okay? So, the risk of accepting a gamble, first of all, what we learn from this depends on how rich you are, what is your wealth, okay? When you have very little wealth, it's risky to take the gamble. When you have a lot, it's not risky. The question, is there some intermediate point between 100 and 1 million where the situation switches from being risky to not risky? Okay? Now, that's not something we should expect to happen. Things usually move continuously, so it's very risky, a little less risky, and so on, that things will move, yes? But perhaps there is some way to identify a cutoff point where something happens, okay? If we can do that, then that will be something nice, and I want to use that as my measure of riskiness. So the program of what I'm trying to do, of what we are trying to do, is to identify, okay, let me say it again. So I want to identify for what wealth levels it is risky to accept the gamble, and define the riskiness at exactly that critical wealth level where it stops being risky. Okay? So when you have very little, it's risky to accept the gamble. I keep increasing until you say, oh, now it's no longer risky. Okay? If I can identify this in a natural way, in a reasonable way, I'm going to take that as a riskiness measure. Okay? Because the higher that level is, the more risky is. You need more and more wealth. Okay? So how do I do that? Okay? So I'm going now to take the simplest possible model. Just, again, any way or almost any way, I'm sure. I cannot never make statements anyway, but almost every way one generalizes this, one gets exactly the same result. And I'm going to present it the simplest possible way. And the simplest possible way, think of the following scenario. You start with a certain wealth, W1, positive, okay? Every period, 1, 2, 3, and so on, your current wealth, let's call it W sub t, because it's a time t, okay? And you are being offered a gamble, let's call it GT. And what you can do is to say yes or no. Accept or reject, nothing else. If you accept, then the gamble is realized and your wealth increases or decreases according to the realization of the gamble. If you reject, your wealth doesn't change. Can't be much simpler than that, okay? As I said, it's a very stylized and simple model, but that will not matter, okay? Now, I want to focus on this thing that at every period a gamble is offered. Where do those gambles come from? I have no idea. I'm making no assumptions whatsoever on the sequence of gambles. Okay, the sequence of gambles that are being offered is completely arbitrary. So the gamble that you are being offered at time t may depend on what happened in the past, may not depend. I'm not assuming any IAD. The dependence is arbitrary. It's a completely non-Bayesian world. I'm not making any assumption that those gambles come from a certain distribution, because I don't know. I mean, if somebody can tell me what the distribution of the gambles that are being offered to us, I will be, okay, I won't say anything more about what I think about that statement. We really don't know. We are getting gambles, okay? For the computer scientists, we are in an adversary world where gambles are being thrown at us by some adversary that, you know, probably doesn't like us very much, but who knows, you know? We have to be ready. Okay, forget the technical things. Now, how do we behave in such a situation? I want a simple way of behaving, which means for every gamble, you decide on a certain level of wealth. Okay, a critical wealth level, and you say, look, if I'm being offered this gamble and my wealth is below, I say no. If my wealth is above, I say yes. So I can characterize the behavior of such a simple person, and I call this a simple strategies, by a function Q that associates to every gamble the number that tells me the critical wealth at which starts accepting, okay? And what I want is that this should depend only on distributions, I said, should satisfy scaling, and the simple strategies, as I said, if you are offered the gamble G and your wealth is W, you compute your function, that's a personal function, Q of G. If your W is below, you reject. You don't have enough wealth. If it's above, you accept, okay? Now, notice that this function can take values between 0 and infinity, including infinity. So for example, somebody for which this function is infinity is what? Checking your, anybody wants to guess? What does it mean Q of G to be infinity? Means you are never accepting any gamble, because the minimal wealth that you want to accept the gamble is infinite, and nobody has infinite wealth. Okay? On the other hand, if Q of G is 0, means any gamble you get, you always accept. Okay? And you know, different people can have different Qs, and those are very simple strategies. Okay? Now, as I said, I want to look at something very simple, namely bankruptcy. What's bankruptcy? Bankruptcy means your wealth is 0. Well, your wealth becoming 0 with time, which means when you have less than 1 cent, you are bankrupt. Okay, 1/10 of a cent, you are bankrupt. So the limit going to 0 is bankruptcy. And what we want to do is to avoid it. So no bankruptcy means this event has probability 0. We don't want this to happen. So when am I going to say that a certain strategy guarantees no bankruptcy? If there is no bankruptcy, no matter what sequence of gambles I'm going to face, and no matter how much wealth I start with. Okay? Now, what I want is to characterize the strategies, the simple strategies, that guarantee no bankruptcy. Are there any such strategies? Of course there are, yes? For example, never accepting any gamble is clearly not going to make me bankrupt. Of course, I'm not going to make any money either during my lifetime, but, you know, that's okay. Question, can I do with, you know, accepting a little? Okay, is there some, okay? So it turns out there is a neat characterization of the strategies that guarantee no bankruptcy, okay? And that's a result of this paper that says the following. To every gamble G, you can associate a certain number, which I'll call R of G, a positive number. There is a unique number, R of G, with the following property. If you take a strategy, a simple strategy with a function Q, and you ask yourself, is that strategy going to avoid bankruptcy? Is that strategy going to guarantee no bankruptcy? Answer is yes, if and only if it is above R. So if your rule is that you have a rule that only accepts that the minimal level when you accept is something which is R or above, then you guarantee no bankruptcy. And if you don't satisfy that even for one gamble, then there will be certain sequences of gambles where you are going to go bankrupt, even with probability 1. So it's quite surprising that one can neatly characterize the strategies that guarantee no bankruptcy and those that don't. Okay? And Go back to the previous thing. You showed 8. Okay. Let me, okay, so what it says, to every gamble, so what this theorem says, to every gamble there is a number. And that number, R of G, which you see here, is such that if you use a strategy like this, where you reject when your wealth is below this, and accept here, that's okay, provided you do this for all gambles, okay? So this strategy is okay. Okay, this strategy is okay. If you always reject, you are fine, as we said. This strategy is okay. Anything where you put the Q of G above R of G is okay. What is, okay, so that's what I'm going to define as the riskiness. Because I've identified a minimal wealth level that if you always reject a gamble when you are below, you'll never go bankrupt. If you sometimes do, you'll go bankrupt. Of course, there will be situations where you'll go bankrupt, okay? So no bankruptcy is guaranteed, in words if and only if one never accepts gambles whose riskiness exceeds the current wealth. If we take this R of G as the riskiness. So you have a certain number. If whenever you are below, you reject. I'm not saying when to accept. When you're above, I'm not saying accept. Then you decide when to accept. Maybe never, maybe sometimes. But when you are below R of G, you should reject. That's a necessary and sufficient condition to guarantee no bankruptcy, okay? And lo and behold, it's exactly the equation that I gave you before. It's a unique solution of this equation, okay? And again, I'm not going to get into details. I don't have time for that. Okay, and I'm going to skip all this, which explains where this number comes from, and satisfies all the good properties you want, in particular stochastic dominance. So let me just summarize what we have here. We have identified for every gamble a number R of G, okay, which is objective and universal, okay? Utilities didn't appear here. There are no utility functions in all this story. Okay, I hope that you forgot the first part temporarily until I'll put everything together. In this part, you just have wealth, and you have gambles, and you have a certain rule, when to accept and when to reject, and I'm asking which rules work and which rules don't work. And work means guaranteeing no bankruptcy. So what happens is that that R of G really, maybe I should, it's not here, but I should really say, there is a clear-cut change of phase. Below it, things are bad. Things go to zero. In fact, even exponentially. Above it, things go to infinity. And there is a clear-cut change of phase exactly at that number R of G. It's not just, therefore, it doesn't really matter if one talks about the bankruptcy model or some other model where you have shares or some other model where you just want to make money or not lose money. Any condition that you'll put there and any generalization, any reasonable generalization of the model is going to give you exactly the same critical point, exactly the same place where there is this change of phase between going down and going up. Okay, so it's quite surprising that there is such a sharp distinction, and that happens for every gamble G at the number R of G. Okay, so this, as I said, it's objective and universal, doesn't depend on utilities, risk aversion, anything. Okay, has a clear operational interpretation, good properties like stochastic dominance, monotonic with respect to stochastic. So this thing that sigma, that standard deviation did not satisfy, now it is neatly satisfied. You increase gains, decrease losses, have less lotteries, riskiness goes down. Okay, no problem. Okay, and I think it may be quite a useful tool. Perhaps one should start, doing finance with R instead of sigma. Okay, and some people are trying to do this, by the way. I mentioned Oad Kadan, that was also a student at the center, in fact, many years ago, and he's working on these things. I'll say something about VAR. Now I have 5 minutes. Yes? 3 minutes. Okay. Axiomatic. So now forget part 1, forget part 2. We're starting from scratch. Okay? And the last minute I'll put them all together. Okay? So axiomatic approach says this. Look, I want to define riskiness. How would I define riskiness? I don't know what riskiness is, okay? Again, it's joint work with Dean Foster. So So we need some interpretation in mind. So some interpretation is something like a wealth requirement. So for every gamble, there is a certain wealth requirement. You'll try to invest into a hedge fund. They'll say, wait a minute. I mean, at least the reputable ones. Do you have $1 million or do you have $5 million? If you don't have that, you can't invest. Okay? So there are certain wealth requirements for getting into certain risky endeavors. Okay? Or you want to, to bid for a certain project. Do you have enough wealth? To get into that project, because you may lose, you may gain. We have to know, and so on. So wealth requirement, reserve, cushion, all these words should come to mind, okay? Now, how to define this exactly, I don't know. At Basel, they sit and they will sit Basel 1, 2, 3, 15, and so on, and not resolve it. So let's try to go axiomatically. Let's think what such a requirement should do, okay? So what we want is to associate to every gamble a number, Q of G. And here are the axioms. Let me go over that quickly, because the axioms are very, very simple. They should depend only on the distribution. So I don't care in what instance you get $100. I just care with what probability you get $100, okay? Only values and probabilities matter. Should satisfy scaling. In fact, that's important. If you'll ask me during I won't have time to get to it, but this here has a neat non-manipulability interpretation. Okay, monotonicity is first order monotonicity, says you increase gains, decrease losses, that requirement should go down. Those are all clear requirements, and there is one that really captures this, that it's wealth requirement, and let me explain that. That will be the last thing I explain. Take this gamble G, plus 200 minus 100, I don't care on the probabilities, and let's assume that if you gain 200, then you are going to face another gamble, H1, with some outcomes. And if you lose 100, you are going to face another gamble, H2. So you have a compound gamble, okay? Now let's assume that the wealth requirement for the first gamble is 500. So to take the first gamble, you need 500. That's a wealth requirement. Let's assume that the wealth requirement for H1 is 700. For the sharp ones, I think that's still level 1, yes? 700 is 500 plus 200. H2, the wealth requirement is 400, which is 500 minus 100. So what does it say? The wealth requirement for the original gambler was 500. Then, if you make 200, now you have 700. So you can afford the gamble where the wealth requirement is 700. On the other hand, if you lost 100, your 500 became 400, so you can only afford the gamble whose wealth requirement is 400. Now, if we have a compound gamble with this property, what is the wealth requirement that is needed for the whole thing? 500, because you have 500 to start, and no matter what happens, you'll have the right amount to continue. Okay, that's the axiom. That's a compound axiom on wealth requirement, okay? Let me not get into details because I do not have time. So let me just tell you the result here. Let's look at all functions that satisfy the axiom that I said: distribution, scaling, monotonicity, and compound gamble. Turns out that there is more than one function. But in fact, all these functions, we characterize them, they are well ordered, and there is a minimal one. And the minimal one, you'll probably not be surprised, is exactly the Foster-Hart riskiness measure. Okay? So what it says is that the Foster-Hart riskiness measure satisfies these 4 axioms, and any other function that satisfies it is strictly above, in fact, for any gamble. So that's a minimal wealth requirement. Okay? Do I have time for that or not? No. Okay. So you can read it on the web. Okay. So summary. Okay, let me summarize. So what we're doing, we're looking for an objective way to measure riskiness of gamble, and I emphasize objective, because, I still get referee reports saying, oh, I asked in class 3 people and they told me that one likes this and the other likes that. Sure, you'll also ask people in class if they prefer a gambler with expectation this or expectation that. You'll get different numbers, but that's not the right answer. This is an objective measure, not a subjective measure. It's something that measures objectively the riskiness content of a gambler. It's like expectation. It's like, I'm repeating that slide. Expectation, standard deviation. This is like a parameter of the distribution. It's an objective measure. Okay, and that's what we obtain. By the way, VAR here is not for variance, but it's value at risk, which is an even worse thing. It's the simpler thing to manipulate, and that has been heavily done in the latest, and it's heavily manipulated in a most trivial way. Any kindergarten kid can manipulate VAR. Details, I can tell you. Well, maybe not every kindergarten. So what I've showed you is 3 different approaches to objective riskiness. I'm repeating. One was ordinal. We are comparing gambles in terms of which one risk-averse decision makers reject more, and we get neat, nice, complete orders. There was operational one where we're asking, is there a critical wealth level where something happens? And we have identified that. And there was axiomatic one where we put a set of desiderata and that gave us the same thing. Okay? Now, surprisingly, those things are not equivalent. One cannot go from one to the other. The proofs are completely different. In fact, the axiomatic one, which always is the most simple one, is the most mathematically challenging and difficult, and it doesn't degenerate to one of the others. Each one comes from a different approach, but they all give us the same answer. Okay? And I'm going to end just with one slide, which is, you can look at it. Something I look for on the web on something on intrinsic risk. So it says that this sign has sharp edges, but there is, says down there also, there is a bridge ahead. Okay, thank you. What? Any question? I can't see. Yes. No, but rich people are again, no. The answer in general is no. In certain, that requires certain assumptions on the utility function, which in fact are part of the assumptions that Arrow made, which is that rich people are less risk averse than poor people. Okay? That's an assumption in that model. It's not an assumption in any of the other 2 approaches. So if you want, in some sense, that's what's nice, that you have 3 different approaches, each one with different assumptions coming from different worlds, and you say, well, I don't know what's the justification for that. You don't like, forget it. Go to approach number 2, approach number 3. Maybe there you don't like something, I don't know, but at least you have not to like many, many things in order to rule them all out. Okay? Okay, thank you.